Okay, so we'll start the coding part now. You should have this repository called end-to-end projects. The link to the repository to add this code to your code editor is given to you along with the video. You can click on that link and you'll have this repository which contains this project called flood mapping. We'll start with the script 1A. I'll build the script along with you, explain you along the way, and we'll end up with the complete script that is 1B. And this is the first step, and we'll continue building on that. Ideally, once you watch this part of the video, stop the video, go back in the script 1A and try to replicate what I did and complete the script as I showed you, and you'll end up with the script that is identical to 1B, and then we'll move on to the next part. So here, this is the setup of the project. We want to detect floods, so we want to know when the flood event happened, and this is the information that you usually have from your news reports, from the field reports, where when the event happened, and you should select a period before the image where as a baseline to know what the region looked like before the flood, and you should pick the images, the immediately available images after the flood event. And in this example, I'm showing you, we are working in the state of Kerala in India. In 2018, they had one of the worst flood events in the history. So we are trying to detect the flooded region for that particular flood event. And here the script defines the before and after period. You should have the period to be at least 11 days so that you have a chance of getting at least one sentinel, one image captured there. The period could be adjusted depending on the region, where if you know that the heavy rainfall started at a particular date, you should consider all the dates before that as the before event. And here we have defined some before start and end date, and then after start and end date. And here we've defined the region. This is the district that we are trying to detect the floods in. So I've just taken the FAO call admin units feature collection and filtered it down to the district that I'm interested in, and we visualize this. So now let's just, the first step is to load the Sentinel-1 data and filter it to get the appropriate images for before and after. To start with the Sentinel-1, you can just search for Sentinel-1 in the search box here. This is this SAR GRD dataset that we want to use. So you can see that data is available from 2014 onwards. You can just import it. You can import it as S1. And now we have our image collection here. So let's just apply filter here. I'll just start writing what filter to apply. So the first filter that we want to apply is that, remember I told you the majority of the images are captured in this IW mode, and they all have VV and VH band. But what are the properties that this data is stored in? So before we look at anything, we'll just say this is we'll take the full data set, and let's just get the first image out of this and see what properties are contained. And this is a very useful function, the first function, which will just pull out the first image from the collection. So you can just see and look at what the data is. You can see this has got the HH and HV band. This has got a bunch of properties. And you can see there is this instrument mode property. And here the instrument mode is EW, that is the wide mode. We don't want that. We don't want the IW mode. So we'll just use this property. You can just copy this and we'll just apply that first filter here. So we can just say filter, and this is a metadata filter. So we can just use efilter.eq, paste the property name here, and we want the IW mode. So this is the first filter. Next, we want to have a filter which has got where we only want the images from the collection which have both VV and VH band. And you can see this is a property called transmitter receiver polarization. And this property is the values are a list. So most commonly when you apply a metadata filter, you've used filters like EQ, LT, greater than, etc. But here we need to look in the list and say the list should contain the VV and VH polarization. So how do we do that? And this is where we can use this filter. You can look in the e.filter docs, and you'll find this filter called list contains. So list contains, where this is allows you to look at a property field and say, if this list contains the value of interest, the filter will pass. So let's see how do we write this filter. So we can just say ee.filter.list contains, and this is the property name. And we should say this list should contain, say, VH. And we can apply another filter, same in the similar way. Now, if I run this just after applying those filters, it's good to check as you're applying the filters just to see if your code has any errors or not. And let's see this image. And you'll see now when you get this image, it both will have a VB and VH band. Remember now, since we have filtered it, the filtered collection should only contain the VB and VH band. And this is also an IW mode image. So our filters are working. We are getting the right set of images. Next, we want to, what we need to do is, as I mentioned, the Sentinel-1 data can be captured both in ascending orbit and descending orbit. And you generally don't mix those two data sets. So if you're looking at the before images and after images, if one is captured during an ascending mode and one is captured during descent, the angles will be different. You'll get a very different look at the same place. And you'll get it's not suitable for change detection because anyway, those images will be very different, even if nothing has changed on the ground. So when you're doing this kind of change detection, always filter to a particular or particular type of orbit, whether it's ascending or descending. It really depends on, because those are captured at different times. So you can look at those timestamps and see which one is more appropriate. Here, we'll just go with the descending orbit for this one. So you can see this is the orbit properties pass property. Here we can say, show me only all images which are from the descending orbit. And we can just copy paste the value from here. And certain regions of the world have only descending orbits. Certain regions have only ascending orbits. So, just check your filters. Once you write this filter, check if your filter actually results in any images or not. The next one we need to filter. This is not absolutely required, but just still useful just to ensure that you get the same resolution data. You have this property called resolution meters, and the resolution could be different depending on the different type of processing. We'll just apply a filter of 10 meters to say we'll just end up with a homogeneous collection. This is important because we are doing the difference. We want both the images to be captured using the exact same configuration, and that way we can now do a diff and we'll know exactly what has changed. So that's it. The next one, we should just filter it to our region. So we'll say, give me all the images that are from our geometry. So geometry is the district geometry here. So all the images that match all these criteria and which also cover this geometry. And after this, we'll just select out the VV and VH bands. So those are the two bands we are interested in. So this is all a long filter, but hopefully you understand now what the filter does and how you get to this one. And I just run this once again to see if this results in any images or not. And it surely does. And you can verify this, the properties match what we wanted to do it. So now this filter collection has a whole bunch of images, all both contained, all images contain VV and VH bands. So now let's find out which images are before and which images are after. So we'll just create before collection, and then we'll take the filtered collection and apply one more filter, which is your E filter date. And we know what dates to apply because we have the before start and we have the before end. So now this collection should contain only the images that are before and after. You can print this and see if those resulted in any images. Sometimes if your range is too narrow, you may not get any images. So you need to expand your range till you get at least one image that matches your condition. We can then do an after collection. Say filtered, apply another filter. And this would be after start. Got it. So now we have two collections. And one thing you can do in optical data, usually when we have a collection and we want an image, we apply a median filter. And the reason for, also we apply a median reducer and create a median composite. The reason to do this is that in optical data, the clouds can be a problem. So clouds can be very bright, cloud shadow can be very dark, and they can really throw off your mean value. If you just take a mean, that's very sensitive to outliers like clouds and cloud shadows. But the Sentinel data doesn't have clouds problem. So you could just take the collection and do a mean. Mean works quite well. So if you have overlapping images, you can get a mean value, or you can just do a mosaic. And a mosaic means whatever order of the images, the latest image would be on top, and you'll just get the top pixels out of that. So you'll just create just overlay images on top and take a mosaic of that. So you can do either of them. Here I'm just doing a mosaic. So we can do before collection, sorry, before dot mosaic, and mosaic will turn an image collection into an image. And just by looking at the whatever pixels are on top, we'll just create that. You could use mean here as well. That is also fine. And this is useful where you have multiple images and you just want to take an average value of that. And we'll just clip it to geometry. Same way we'll do our after image, and we'll just take our after collection, mosaic it. And mosaic is important because the clip function is specific. It runs only on images. So if you try to apply that on image collection, you will get an error saying that I can't clip a collection of images. So you need to create an image. So in optical data, you'll do a median composite. Here you'll do a mosaic or a mean. So now we have both before and after. And then, in the next script, I'll show you how to take those images and visualize them. So at this point, you should have a before and after image. You can just print it and just ensure that you have an image here. Sometimes if you're, again, as I mentioned, the date range is too tight or you have made a mistake here, you may not get any images. And you can see now I've got an image here. So that's good. And we are good to go to the next script. So I'll see you in the next video.